we've been talking about the method of characteristics, which is a method for, it's a, explicit, one of our explicit computational methods. And it is a method that you can use to solve a first order PDE. Excuse me. We're gonna, we talked about the development of the material, like the idea and the geometric motivations behind this method. And we worked our way carefully through the linear case, and we did an example. Now let's move up to the semi-linear and quasi-linear cases. I'm going to put them together. That's why I have said that this is at most quasi-linear. So it could be quasi-linear, could be semi-linear. Okay. Either way, if f is first order and quasi-linear, there's only one thing it can be. Remember that quasi-linear, first order means that no derivatives higher than first order derivatives appear. Excuse me. No derivatives higher than first order appear. What about the word quasi-linear? That means that the coefficient of your highest order term can contain u and derivatives of u of strictly lower order. Well, there's only one order that's lower than first order, and that's zeroth order, u itself. So your coefficient can involve both the variable x and u itself. And then you've got some zeroth order terms. And they may be linear, they may be nonlinear. Okay, we identify. You remember how the method goes. You're working in this region in Rn. So you've got your the n variables x1 through xn. Then u depends on that, and then the derivatives of u depend on u, which in turn depends on those xi's. So in this method, you separate them. You separate them. You make them independent variables, and then in turn, then you've got a system. Then you've got a system of first-order equations. Now, if you can identify a special curve, well, let's say this first. Okay, so I'm not going to do too many steps at the same time. Now you've separated those variables. And so you've got your x's, z, that's like the u, and then you've got your pi's. Those are your gradient. But again, you're viewing them as independent variables, not things that depend on u, which in turn depends on x. Okay, so our first step is to identify. I kind of made a mistake here. Look, this is the equation. That's the equation we want to solve. This is f. That's f of x, u, and gradient of u, the first order partial derivatives. This is f. Okay, so now my first step is I identify what is f as a function of those newly invented independent variables. And I've done that while at the same time recognizing this as an inner product. That's not so important. That's not so important. It's just like a way of compressing my notation. It's a little more geometric. I mean, this is a very geometric method. So recognizing this as an inner product is a little, I think it's helpful. Okay, written in terms of those independent variables, x, z, and p, I identify f. Now you remember the method. You want to identify special curves these curves are adapted to the geometry of the problem. And then along those curves, z and p will be functions. Well, the curve in we're here in this region U. The curve is the image of a function back here in your parameter space, S, the real numbers S. Okay, so then evaluated, and then you've got, like U, or Z, and P, and evaluated along that curve, Z becomes a function of S, P becomes a function of S, and then we want to choose that curve correctly, not correctly, strategically. We want, these are the equations, the differential equations, the ODEs that you want the xi's to solve. It's like this. I mean, we did this in detail before, but just briefly, it is like this. You want the velocity vector. You want the velocity vector of this curve. You want the velocity vector of this curve to be this vector b. Okay? Then we'll derive the, let me erase the board and I'll derive the equations that the pi's and the z should satisfy. Okay, now I want to make a couple of observations, and we can compare this quasi-linear case to what happened in the linear case, and then we can anticipate what's going to happen in the fully, if we move to the fully nonlinear case. In the linear case, okay, remember what the difference, remember where these things came from. To be quasi-linear, so this is a first order equation, so the highest order terms that appear are first order. To be quasi-linear means that the coefficient of the highest order term can involve u and its derivatives of order strictly lower. That means in this case, since it is already first order, that means u itself. That's why in this vector, written in vector notation, I mean the components of this vector are those coefficients. First of all, writing it as a vector, it just gives me a way of compressing the notation a little bit, but it's more than that. It's a very geometric notion, and it's helpful to think of it, geometrically. This is my velocity vector. I want it to agree with that vector b. But notice that the b, compared to the linear case, in the linear case, b involved only the curve itself. And so you could, so then you had, written in components. Gamma, the curve gamma, has components x1 through xn, each of which depends on s. So written in components, it's this, right? In the linear case, bi depended on just, bi involved just the x, just the variables x1 through xn. So you could solve, why am I writing the left-hand side in terms of components and not the right-hand side? If I write it out in detail, that's what it looked like. That's what this system looked like for the linear case, right? And you can solve this system right away. You can solve this system right away, and then you've got your curve gamma. Here, but knowing the curve, I mean, of course it's very important, but knowing the curve itself is never enough information, because then it's u that solves an ODE along that curve. Still, it's a lesser level of complexity. Now here, in the quasi-linear case, Z also appears, and so you have a greater level, greater degree of interdependency in this system. But you know, I mean, if you can solve for the curve and solve for Z, that's all you really need. That's all you really need, right? So let's look at the equation for Z. From the general development that we did the other day, dz ds should satisfy this equation. Written, the coefficients, the df, dpi, those are your b's. And so again, written in recognizing that this is equal to bi, and then writing it in, recognizing it as an inner product. I can write my equation this way. This is dz ds here on the left-hand side, right? This is dz ds here on the left-hand side. How does this depend on s? This is your inner product, but it gets evaluated at this point on the curve, which ultimately, right, the curve is the image, which ultimately depends on the parameter s. Okay, so that's dz ds. Now, remember that remember our equation. This is the original equation. This is the original equation that we are trying to solve. And so these two come from this comes from the general development. From here to here, all I've done is write it, recognize what is df, dpi, and then write it in as an inner product. Now, to get from here to here, remember that this is the equation you're trying to solve. That's the equation you're trying to solve. And so, this inner product of b with p is equal to minus c. Again, how's that a function of s? How's that a function of s? C gets evaluated. C in the original depended possibly on x1 through xn, but they lie now along the curve, right? x1 through xn, and C might have involved u. That's our newly independent variable C of s. So that's your equation. That's your equation for dz ds. In the linear, so both in the linear and the quasi-linear case, this system, you've got n plus 1 equations. This always has to be solved because you need the curve and you need to know the differential equation that your solution function u satisfies along the curve. So those always have to get solved. And again, here observe the higher level of interdependency in this system. The linear case a little simpler because there was no explicit dependence on z, and so you could solve those equations right away. Okay, well, and then they go into the equation for z. But z is just a real valued function. You don't have it. It's not. That one is a single equation. Once these are solved, this is just a single ODE. Now think about, like, when you trace back and you think about where this dependence came from. This z appeared because the coefficients of your first order term involved u. Now think about what would happen if you were in the fully nonlinear case. In the fully nonlinear case, you might have products. You might have products of your highest order terms. So you'd have terms like products of the PIs. You'd have products of the PIs. And so this, df, dp, sorry, let me not, I'm not going to go on to z before I finish with gamma. In a fully nonlinear case, these coefficients, you'd have dependence on p also. And so in the fully nonlinear case, the whole system, the equations for the PIs have to be solved. So the whole system consisting of 2n plus 1 equations needs to be solved. Of course, the P equations only need to be solved. The P equations only need to be solved in order that these be solved. But as I said, that's the difference. You can see the hierarchy of, like how bad it can be. Okay, okay, those are the equations. In the quasi-linear case, that's all we need. We're not going to think about the logic. Think about the direction of the logic. It's the direction of logic started like this. If U were a C2 solution, and if you could find this curve gamma, then these equations would follow as a consequence. And we're going to do, I hope it will help. We're going to do a little in-class activity that's exactly like that. We're going to, just to like reinforce and like solidify this, the direction of the logic, because you can sometimes feel like you're going around in circles. We're going to do a little in-class activity next week where we're going to start with an equation that we have already solved by other methods, and then we're going to verify. Then we're going to find the curve, and we're going to verify that indeed these equations hold. Okay. As I said, the PI equations follow as a consequence, and in the quasi-linear case, those equations don't need to be solved. They only need to be solved in order that you solve the equations for the curve and for the function u along the curve. Okay, let's do an example, and starting this example reminds me of something that I knew there was something else I wanted to say previously, and the example reminds me of this point. Okay, so let's do an example. I got this straight out of the book, out of the textbook of Evans. du dx1 plus du dx2 equals u squared, and so our region, capital U, is the upper half plane. And we want u, this is a boundary value problem, we want u to equal g on the horizontal axis, which would take the notation, gamma. Okay, here's what I wanted to say. It's related to the point I was making about, the direction of the logic. So, sometimes it's easy to feel with this method, but it's so common in PDE, it's easy to feel like, you're going around in circles, because to derive the system of equations, we differentiated the original equation itself. And as I said, you can feel like you're going around in circles, and sometimes I do. Well, first of all, that's the only thing you have to work with is the equation. And so when I do these problems, instead of just diving in and like calculate, I could just memorize or look them up, find the formulas or the system. But me, I just do the method every single time. I do the method every single time so I can keep the logic straight, but also, of course, there's always another motivation too, which is that, we're not just trying to get through the homework. It's not a question of just like solve this homework problem and, put it aside and go on to the next thing. We're trying to learn these methods, for all time, so that later, deeply internalize them, so that later when we're doing our own research, we're like, oh yeah, and it even happened to me with this very method. I was reading a paper, my friend and I are working on a problem for, you know, kind of related in this area. That's why it's reading the paper. And I was like, oh yeah, you know, this reminds me of the method of characteristics. For that, I need to have, you know, kind of like internalize this picture, and that's why it's kind of an investment. It's kind of an investment. When I do the, I mean, it's not homework, like I'm not going to turn this in for me, but it's homework in the sense that I am preparing. I'm doing the same thing you are doing. I am preparing for our class. So when I do a problem, I do the method every single time. I do the method every single time. Okay, so let's do the method. First, you write this in the form. You write this in the equation in the form. And you got to match it up. You got to match it up in order to identify. Here's f. I've written it in the form f equals 0. And then I identify. Now I'm separating what you know, quantities that used to depend on other quantities. I'm separating them out into my independent variables, and I recognize, I identify, here's f, written in terms of those independent variables. Now I start the method. My starting point is, here's my region. Oh, I've already got my region. Here's my region. If I had a function, if I had a curve in this region, the curve is the image of a function, right? And if it touched the boundary, that's the hope. Then along that curve, so here's my image point, and it has n coordinates. Each one of them depends in turn on s, back in the parameter space. Okay? Along the curve, then my newly independent variable z. Okay, and again, you can feel like you're going around in circles, because you're like, well, just a minute ago you said z is independent, but now you're saying it's u, which depends on s. Okay, again, you got to keep this logic straight. But this is the reasoning. If, because that's the starting point, if a solution existed, then z would depend on s in the following way. P would depend on s in the following way. And then, here's the key you got to remember. And this, you know, this is where it's good to have the picture in your head. I want to choose the curve gamma strategically. I want to choose the curve gamma strategically so that its velocity agrees with the derivative of f in the p direction. Go back. Oh, okay, the calculation is very easy. Go back to the original equation. df dp1 is 1. df dp2 is 1. So written in coordinates, my velocity vector should be equal to 1, 1. That's a system that's really easy to solve. We talked, by the way, a moment ago about how in this the z, this system, it can be solved and right away. There's no dependence of this on z. If you look, if you think about why that happened in this equation, go back to the in this example, go back to the original equation. This problem is actually only semi-linear. It's not truly quasi-linear. And that's why we've got a system that we can solve right away. And I would do it, except that my board is so small. Not just for my, it's not just for my low vision students that I try to, write so big. But I know that you'll be peering at this, peering at a laptop, and I've even seen some of you trying to do this on your phones. I mean, what's next? A postage stamp? Okay, anyway, I'm going to solve that system. Okay, this is the point we had reached a moment ago. I want to choose my curve in such a way that the velocity vector is equal to 1, 1. I just integrate in each component. My my first component is equal to s plus a constant. My second component is equal to s plus a constant. And so here's my curve. Here's my curve. Now go back though to the problem as it was given. We're solving in the upper half plane, and when you ideally, I mean, of course, you know, if this happened, I mean, you can start to once you start to, you know, get a idea, you know, of you know how this method works, and you notice that some of these examples look like they were really kind of cooked up to work out easily. You can start to feel uneasy and start to think about how it could so easily go wrong. I mean, what if the curve looked like this? You're given boundary values here. Look, fortunately, I mean, again, this is a very simple example. If s equals 0, you want the curve to start, because remember, you're going to solve an ODE along the curve, and the initial value should be given. Then you'll have a unique solution. I mean, you know, I'm talking about, you know, from your undergraduate studies. Okay, so in order that the curves start on the boundary, you want to choose b to be equal to 0. That way, when gamma equals 0, I'm starting here on the boundary. And now look how nicely this works out. Your curves, these curves sweep out the region. These curves sweep out the region, and you can start to think about, you know, how it could so easily go wrong. Those curves never intersect. You can start to wonder, you know, geez, what if they don't sweep out the region, or what if they intersect, and so on. Okay, those are, you know, well, we'll talk about it, but right now we've got other fish to fry. And don't worry, it's just an expression. No actual fish were harmed in the production of this utterance. Let's solve the z equation. If this equation had truly been nonlinear, then we would have had to truly solve a system, because this one might have depended on z. Here it doesn't. This one, dz ds equals z squared. This equation stands alone. I easily solve it. I just solve it by the fundamental theorem of calculus. But here, even here, there's a little wrinkle you got to iron out, which is I want to divide by z squared. I gotta ask myself what happens if z equals 0. Z equals 0, u identically equal to 0 might solve this equation, but the thing is, it will almost never solve the boundary value. It will almost never satisfy the boundary. I mean, if the boundary value happened to be 0, then that's fine. Typically, it won't solve the boundary value. So you just forge ahead. You just forge ahead. Write this on your paper, you know, and okay, look, but again, you know, I've kind of already handled the case where z equals 0. Well, that's z identically equal to 0. It solves the equation, but in most cases will not satisfy the boundary value. It's supposed to be equal to g along the boundary. Okay, but I forge ahead. I solve this by, it's just a fundamental theorem of calculus. I just integrate, and this is what I get. After a couple of algebraic steps, I solve for z. This is no big deal, but let me just mention it, that this solution just slightly different than what is in the notes. What's in the written notes. It really doesn't matter. Okay, here's what we're going to do. Let's deal with the initial value, and then we'll see whether we can this is z as a function of s. As I said, if you want to find, I mean, z is you, it's your solution. But if you want to find your solution at a given point in the plane, and you want to express it as a function, what is u? Like you give me two coordinates, x1 and x2, I should be able to tell you, okay, what is u? You'll need to be able to find the intersection. You'll need to be able to find which curve is it on, and this point is reached at which parameter value. So let's deal first with this question, and then we'll deal with the parameter value and see if at the end of the day we can just express, write down a solution for u as a function of x1 and x2. Okay, we had solved for z, and this is what we got, right? And in some sense, this is the solution u. People won't be very happy about it though, because it leaves it up to them to. I mean, we're going to do it. We're not going to leave it up to them, but it is in some sense a solution. But you've got to find s and z of 0 and so on. So let's do that. Let's do that. And see if we can, how we can express our final form. Well, z of 0, let me see, z of 0, that's u evaluated at gamma of 0. Right, remember gamma? So let's say like this. In fact, let me number it. Let me number it sequentially or chronologically. Say you give me a point in the plane. So I start there. Now, I want to know for which, and this is what my curves look like, remember? So I want to know on which curve does it lie, and at what parameter value is it reached. We wrote, listen, we wrote gamma of s. I mean, if you really wanted to, you could write like gamma lower a of s, because it's really a whole family. We really solve for a whole family of curves. Okay? I mean, maybe I won't write the little a in, but as I said, it really and truly is a family. Which curve? I'll write it here. So which curve does it lie on? Then I want gamma of s to be the curve to reach x1 and x2. And this will happen if and only if s plus a is equal to s1 and s is equal to x2. If s is equal to x2, then a solve a has to be equal to x1 minus x2. So if you start here with the given point, this is the unique curve. This is the unique curve. This is the unique curve that passes through that point. If s equals 0, we already chose b. That remember there was originally constants of integration appearing in both variables. We already chose b to be 0 so that all of these curves, every one of the curves in this family, starts on the axis. This is the unique one that starts on the axis and passes through the given point x1, x2. Okay, what is this point? This is the unique curve at 0, gamma of 0, again, you could write it gamma lower a of 0 or whatever, because it's, I'm not going to, muddy the waters here. This point is x1, substitute in s equals 0 here. It's like x1 minus x2, 0. All right? That's the point. Let's label that 3. That's the point at which that unique curve intersects the axis. Okay, so now we can find, so let's go back to here, which is in, as I said, it is in some sense our solution, but and yet it leaves so much, to have to be solved separately. So let's do that. Not gamma, z of 0. Z of 0, that is u at the starting point gamma of 0. So it's u evaluated at the point x1 minus x2 comma 0. Now, the value there was given on the boundary. This is a boundary value problem. On the boundary, u is supposed to be equal to g. I'm thinking of g as g is defined here on this one-dimensional set. G is defined here on this one-dimensional set. So I'm kind of thinking of g as a function of one variable. There would be nothing wrong in viewing g as a function of two variables and writing, you can write g of x1 minus x2 or write g of x1 minus x2 comma 0. Okay? I'm thinking of g as a function that is only given, or it's a function of one variable, only given on the horizontal axis. Okay, whatever. Okay, then, that's not in it. This is a crucial point. I substitute that into the solution that I got for z, all right? But that still leaves, I have to identify for what parameter value. That's z as a function of s, which is u evaluated at gamma of s, right? U evaluated at gamma of s, and we already solved, you reach this point, x1, x2, when the parameter value is equal to x2. So finally, as a function of, as a simple function, you give me the coordinates x1, x2 at a point in the region u, and I can give you the solution. This is what it looks like. You got to be careful because this denominator could, in principle, well, we don't know what g is yet, but it could, in principle, be 0. So you just have to say that, if g is known explicitly, then you can just solve for the values of x2 that make that denominator equal to 0, and then you can say that, in that region, that the solution does not exist. Elsewhere, here's your solution in a nice closed form. You probably started to feel as we went through these examples that number one, the examples were cooked up to be, there was a reason I took them straight out of a textbook. They were cooked up to be, number one, the computations weren't too bad. But number two, but you also I'm sure you also perceived, some more serious problem, things that could go wrong. Like, it's just so astonishing, that these curves sweep out the whole region, right? And they never intersect. Each point x1, x2 lies on a unique curve. How convenient. And as you go along, you might keep in your mind, or even better, maybe write it down in your notebook, a little list of what could go wrong, what can go wrong in this method. And we'll look at some more examples, and we'll start to address some scenarios in which it's maybe not so straightforward.